Okay, today we're introducing some calculus topics and especially the notation. Okay, so notation means how we write these kind of things. What does it look like? Right? Mathematics is full of notations, and being able to understand and interpret and read those notations and translate them into layman's terms, right, normal English, is something that usually takes a little bit of time. So to introduce it, we have this function, right, this rational function, whose graph is over here. It has an asymptote at positive 3. It has a hole at negative 3, and here's the coordinate for the hole, negative 3 comma 7/6. And then it has a horizontal asymptote here at positive 2. Okay, so we're going to take this rational function and use it in order to write our calculus limit notations from our pre-calculus statements. Okay, so as x approaches negative infinity, right, if we're talking about negative infinity, we're looking at the left side of the graph. So on the far left side of the graph, what is the y value starting to get close to? Starting to get close to 2. And how do we know it's getting close to 2? Because it is a horizontal asymptote, right? So limits to infinity, when x is going to infinity, are horizontal asymptotes. Okay, now what that would look like in calculus in limit notation is we would write the word lim, representing limits, and below the lim is where we put our x going to negative infinity, right? What x are we talking about? And then our function was called f, so we're talking about f of x. The limit as x approaches negative infinity for your graph is positive 2. Right? That's the y value that goes along with this. All the time, the limit is going to be a y value from your graph. The answer to every limit equation is a line or a y value from your graph. Okay, as x goes to positive infinity, we are looking at the right side of your graph. So on the right side of the graph, what is the graph approaching? What is the y value? And again, this is going to positive 2 because the horizontal asymptote goes to the left and to the right. So our notation would simply be limit as x approaches infinity, positive infinity, the y values are going to positive 2. So limits to infinity are talking about horizontal asymptotes, and what are the y values approaching as x's are getting very large negative or very large positive values. Okay, so now we have x going to a number, negative 3. So let's follow the graph as x approaches negative 3 from the left. Okay, so as we approach negative 3 from the left, what is the y value we are trying to get close to? Okay, well, so what are we trying to approach graphically speaking? What is this thing right here called?
A hole.
That's a hole. Okay, do we know what the coordinate for our hole is? Yes, we sure do. So what is the y value? 7/6. Okay, it told us exactly what that y value was. So rather than guessing or guesstimating, we're going to put it in exactly from the information that we were given. Okay, so then we would write from the left. So we would put a little minus sign, like the power. It's not really a power, it's just letting us know that minus means approaching from the left. Okay, of this function, oh, sorry, that needs to be a negative 3 in here. Negative 3 from the left is 7/6. 7/6. That's the y value that x is approaching at negative 3. Okay, even though there's a hole there, right, it's not really there. It's getting really, really close to 7/6 because it's infinitely small. Okay, and from the right, the graph is going to what number? Also 7/6. And our notation would be the exact same, so limit as x approaches negative 3. But now from the right, we put a plus up there. So a minus represents coming from the left, and a plus represents coming from the right.
Oh, so we only put the minus and the plus.
Okay, as x approaches 3 from the left, the graph is going in what direction? Looks like the graph is going down. So how do we represent down forever as a symbol? Negative infinity. And then as it approaches from the right, how do we represent up as a symbol?
Positive infinity.
Positive infinity. Okay, so your limits will look very similar. So limits approaching positive and negatives infinities there. So how might you informally define the value of a limit? Which value are we talking about when we're finding a limit? An x, y, which value? A y value. We are trying to find a y value. What is the y value that the graph is approaching approaches APP as x does something, right? As x goes to infinity, as x goes to a number, as x comes from the right, as x goes to the left, right? What is the y value that the graph is approaching as x is doing something? So for a limit to exist, the left side limit must be equal to the right side limit, right? Your graphs are going towards the same points. And that point happens to be a real number. Okay, so not infinities. Infinities don't count as real numbers. Okay, so let's come over here and look and see an example of a limit that does not exist. So limits that do not exist. So looking at this graph, what is the limit as x approaches 2 from the left? From the left, as x approaches 2, where is the graph going? To positive infinity, right? The graph is going up and up and up without bound, going to positive infinity. And what about from the right? It's also going up to infinity. But what is the actual y value when x equals 2? How do we write that as far as a y value goes? Something over 0, right? An asymptote is going to be undefined. Okay, whenever we have an asymptote on the graph, the y value there is undefined at that x value. That's why there's an asymptote, because it's undefined. Okay, so does the limit exist here? It says the one from the right and the one from the left match up. They both go to infinity. So does the limit exist?
No.
The answer is no, because infinity is not a real number. Okay, not exist. Infinity is not real. Okay, the left and the right have to go to the same spot, and they do, but infinity is not a real number. So it does not exist. Okay? So a limit would not exist if you have an asymptote. Limits do not exist at asymptotes because asymptotes are undefined and infinitely limited. Okay, how about example 2? What y value is the graph approaching on the left of positive 2?
2.
It looks like the y value is indeed going to be positive 2. And what about from the right? What is the y value that the graph is approaching? Also, positive 2.
Also 2, yeah. To the right of the hole, right?
To the right of the hole, yes, as the graph comes down towards the hole, what is the y value that the graph is going towards?
2.
Right, it's going towards positive 2. But what is the y value when x actually is 2?
Wait, isn't it a hole at the top?
Negative 3. It is a hole, but they have defined this equation, right, piecewise definition, that if x is ever 2, the answer is going to be negative 3. Okay, so they have defined this one, that when x is 2, there's a dot, right? The dot represents the point. So when x is 2, y is negative 3.
So if that dot wasn't there, what would it
If that dot wasn't there, then it would be undefined, yes. The y value would be undefined if that dot weren't there. Okay, but so does the limit exist at positive 2?
Yes.
Yes, it does. And why does it?
They both go to the same spot.
-3 is a real number.
And 2 does exist.
Yes, because of this thing right here. The left side goes to positive 2, the right side goes to positive 2, and positive 2 is real. So what is the limit at positive 2?
-3.
Well, that's the y value, but what's the limit?
Oh, I don't know.
Right? It's this number. The left and the right are going here. So this is the limit right there. Okay, so even though the y value is not the same as the limit, that's okay. The graphs are going to here, right? The limit from the left equals the limit as x approaches 2 from the right. And that answer is going to be 2. Okay, because that's the limit from the left and the right. Okay, so sometimes the limit doesn't matter about the existence of that point. Okay, the y value at the point does not have to be the same as the limit, right? What the graph is going towards does not have to be the same as the y value.
So if I said yes because they both go to 2, does that count?
Um,
Do I have to write it like that?
you should write it like calculus.
Alright,
Okay, the people that are reading calculus, your tests are going to want to see the calculus. Yes, but in your head, right, that's what it means, right? And that's where it really counts, is the meaning in your head. Right? What does it mean for a limit to exist? The graph from the left and the right go to the same point. And how do you write that calculus-wise?
They have an F or Q in like calculus, so how does that make sense?
And then lastly, look at our last graph. What is the limit from the left of this graph? Up here. So here's our left, so we're coming in this direction. What is the y value right there? Positive 3, right? The graph on the left of positive 2 goes to positive 3. And what about from the right? So that means we're coming in down here, right? This is the right side of the graph. It's approaching negative 3. Okay, and then what is f of 2? What is the y value exactly at 2?
3.
It is positive 3, right? This is the y value there.
So should we just ignore the arrows on the outside?
Well, this means that the graph continues to go on this direction.
But we're going from the other way.
But we, in our brain, we are approaching it coming like this. We're approaching it from left to right. Right? The graph goes on forever in left and right direction. Right? We just happen to have the arrow there to let you know that the graph goes on forever. It doesn't doesn't have a restriction on the domain from -3 to whatever. It goes on forever. Okay, but you have to move your pencil either left on the graph or right on the graph, no matter where the arrows of the graph go. Okay. So does the limit exist at positive 2?
Yeah.
Is the right side and the left side going to the same number?
No.
No, the left side goes to 3 and the right side goes to -3.
So no.
So no. Okay, this is what we call a jump discontinuity. A jump. The y values jump from positive 3 all the way down to -3. Okay, so if we ever have a jump discontinuity, the limit is not going to exist at the point where the y values jump. Okay, so we would say that the limit as x approaches 2 from the left does not equal the limit as x approaches 2 from the right. Okay, that's all the justification that we need. It is not equal. Okay, so the limit doesn't exist during a couple of places. Number one, an asymptote. Right? Limits do not exist at asymptotes. They do exist at holes, though. Okay, limits do exist at a hole, like they did in example 2. They don't exist at asymptotes, and they don't exist at jump discontinuities. So as long as the graph is continuous and connected, right? The limit will exist. You're just looking from the left side and from the right side. Are they approaching the same numbers? Okay, there you go.